So hello everyone. So we've got Michael Schapira visiting us from the Hebrew University of Jerusalem. He's done quite a bunch of very exciting work, and his current interests are at the intersection of computer networking, machine learning. Before Hebrew University, he was at Google NYC Infrastructure Networking Group and at UC Berkeley, Yale University, Princeton University. He's won the Wolf Foundation Krill Prize, faculty awards from Microsoft, Google, Facebook, IRTF Applied Networking Research Prize, William Bennett Prize for Best Paper at PON, NSDI 2023 Best Paper Award. So very lucky to have you here, and over to you.
Thank you very much. Thanks for the invitation. Thanks for the introduction. And I'm actually visiting currently from the University of Cambridge, where I'm doing a 2-year sabbatical. I'm hosted by John, so I'm in the area. If anyone wants to brainstorm. And I wanted to talk about much of the work I've been doing over the past 8 years or so about trying to apply ideas for machine learning to networking. And of course, this is a conversation. So if you have any questions, comments, insights, just let me know. So the starting point for this is really that there's no need to elaborate on how much ML has impacted other fields in computer science, right? But when we talk about networking, and when I say networking, I don't mean, say, anomaly detection in networks. I mean the core protocols that enable us to deliver traffic across the internet. It's barely left a scratch, right? We're doing routing in pretty much the same way. We're doing traffic engineering in pretty much the same way. And the question is, will this change? And I think this is why it's fascinating to be in this domain now, because we don't yet know whether we're the dinosaurs waiting to be hit by the asteroid, or this will pass and we will all just remain ourselves, right? Pretty much. And the answer is probably somewhere in between. So when we talk about machine learning and networking, we typically mean one of two things: building networks for machine learning, which is a fascinating direction. We've seen a lot of recent work in both industry and academia about this, but I want to focus on the opposite direction. Can we leverage ideas from machine learning to improve or can we apply them to core networking challenges? And specifically, I want to focus on two of the arguably most fundamental networking challenges. One being routing, right? Determining which routes my packets should traverse. And the other one being congestion control. Namely, how do I determine who speaks when? How do we allocate the bandwidth between competing centers of traffic? So this is something I've been working on a lot in recent years, as I've mentioned. And not only are these challenges very different, but they also come in a lot of different flavors. Right, so routing across the internet is different than routing within a data center, which is different than routing between data centers. So I want to talk about one flavor of routing, which is routing within a private WAN. And I want to talk about one flavor of the many different flavors of congestion control, which is internet congestion control, sending traffic across the internet and not, say, within an organizational network. And the reason I want to talk about these two is because I view them as more or less two extreme points of the spectrum, right? When routing within a private WAN, think of the network interconnecting Google's or Microsoft's data centers. When thinking about this network, we really have a single agent that's charged with determining routes across its own network. The decision-making pace is relatively slow. It's of minutes, right? That single agent has a global view of the network. Right? And not only that, but there's a lot of, as I'll try to convince you, stochastic regularity in the environment, which gives rise to opportunities for using statistical machine learning and stochastic optimization in this context. Internet congestion control, in some sense, is the exact opposite. Right? We have multiple interacting agents. They hardly know anything about each other. They only interact with each other indirectly through their traffic. There's a lot of global considerations we need to care about, like stability and fairness, because of the fact that we have these different players interacting with each other. feedback loop for decision-making ranges between milliseconds and tens of milliseconds in most environments. We need to care about worst-case guarantees and not just stochastic guarantees, because there's a daunting breadth of environment in which a congestion control protocol can find itself. And this, I would argue, means that we need to look at a different area in machine learning if we want to employ such tools for improving networking, namely multi-armed bandit theory and online learning, which is also closely related to work in game theory. So I want to talk about each of these and explain why I think that drawing ideas for machine learning is useful. So we have a lot of services sending traffic across the internet. And in between services and consumers, we have the internet. And the chaotic nature of the internet, what's sometimes known as the last mile network, that is all the segments between where the content resides and the end user, is the #1 reason for bad quality of experience. This is why we don't watch every movie in HD. This is why we have lag behind live in live sports. This is why Zoom calls stall occasionally, right? It's because we have a chaotic network, we have intermittent congestion, we have routing changes, we have physical layer effects, right? And the sender, who typically doesn't own the network, like think of Netflix sending traffic through Comcast, right? The sender, who typically doesn't own the network, has very little visibility and no control over what goes on within the network. From the sender's perspective, it's a black box. And this brings us to basically the most fundamental decisions, or maybe the only decisions made by the sender, which are how fast to inject traffic into this black box interconnecting the content and the end user. And this is the classical challenge of congestion control. We have different senders, they're sending traffic across the same network infrastructure. Bandwidth is limited, and the challenge is deciding how fast data should be transmitted. If I send too slowly at a certain point in time, this will harm performance. Think of, if I don't send fast enough, think of video streaming. I won't watch the video in HD simply because I'm not getting sufficiently many bits across the network. If I send too quickly, I'll overflow the network. Packets will be lost, packets will be delayed, and this will again result in bad user experience and of course, network inefficiency. So when we talk about internet congestion control, I'm biased, but I view this as one of the hardest problems in computer science in general, which I think is why it's persisted for so many decades. It's because we have senders, they're sending packets across the network to receivers and receiving packet acknowledgements, but they're competing with others, right? The network is highly dynamic. Flows enters and flows enter, flows leave. The routes might change, as I mentioned, physical layer effects, user mobility, and so on. The topology definitely doesn't look like this most of the time. We have a very complex topology. It's inherently decentralized. I make decisions with basically no knowledge of even the existence of others, let alone the network infrastructure and its topology. And I'm only making these decisions based on a trickle of information in the form of packet acknowledgements arriving from the other end. So the abstract question we started with, which is simple, but I think is worth investigating at this level of abstraction, is what is the right rate to send at? And again, a pretty basic realization is, if you want to be able to answer this question, you have to have some notion of what good means, right? What good performance means, which is absent from most congestion controllers. And I'll explain what I mean by this, but when I send at a certain rate, I want to be able to derive a performance score. Right? I want to say, these are the empirical consequences of sending at this rate. And this was the starting point for a research project that we started in 2015. This is in collaboration with Brighton Godfrey's research group at the University of Illinois at Urbana-Champaign, called Performance-Oriented Congestion Control, where the key idea is I want an explicit notion of utility. to be embedded into the protocol. I want to think if I'm sending, say I'm transmitting a video to you, the way PCC views the world is as a sequence of micro experiments. In each experiment, I send at a certain rate, say 10 megabits per second. And then I want to be able, based on the feedback I get from the other end, to translate this feedback into a performance score. This is what we call the utility value. So the starting point is being able to associate actions with consequences. So I think this is in hindsight obvious, but if you think of protocols like TCP, right, they don't operate this way. They have hardwired responses. If a packet is dropped, I have my transmission rate. Why? Because, right? Because that's what's prescribed. It doesn't matter. I have no notion of my own utility, which I'm trying to optimize. So let's talk a bit about PCC's utility framework in more depth. As I mentioned, when PCC transmits traffic, this is basically a sequence of micro experiments where each experiment is trying to evaluate the empirical performance benefits of sending at a certain rate. I send at a rate of 10 megabits per second. After a while, I start getting packet acknowledgements from the other end, at which point I can start deriving meaningful statistics. Like I was sending at 10 megabits per second, but traffic only arrived at you at 9, right? 0.5% of my packets were lost. While I was sending, the latency between us increased from 12 milliseconds to 17 milliseconds. The next step is aggregating these statistics into a numerical performance value. So think of this as the performance score. So this is the utility function. You can ignore the equation, but the point is the utility function explicitly quantifies how different metrics for evaluating performance should be weighed against each other. If I'm latency sensitive, I would want to penalize latency inflation more, right? If I'm not, I would have a lower value for latency penalty and so on. So think of the utility function as an explicit notion of performance quantification. Yes?
But the utility function could be conveyed or convert.
That's true.
You're going to talk about that.
Could be and should be.
Yes.
Yes.
Right, okay.
Yes. So you're absolutely right that if you were to just know that the reason that I mentioned before that we wanted mathematical foundations and we wanted to be able to reason about the provable guarantees, this is where this comes in. If you were to just choose the utility function, you might get horrible consequences. So I'll get back to this point actually almost immediately. So the other ingredient to PCC is, say that I've sent at a certain rate, I got performance score U1. I sent at a different rate, I got performance score U2. I should have some online algorithm for determining what the next experiment should be, right? So I'm constantly transitioning between rates based on the previously observed empirical consequences of sending at previous rates. Yes.
So what is an experiment here? Is it a portion of time? Or
Yes. Think of roughly. Think of roughly experiments as being RTT long, right? Because I have to wait long enough for packet acknowledgements
It's
to arrive
not
from the
different
other
parts
end.
of a given rule.
No, because I can control these. I'm basically just sending at a certain rate and quantify. That's the R1 here. And after observing the statistics, I know what my performance score is based on this utility function. Then I transition to a different rate. So these experiments are just moving between different rates. And this is where the online rate adaptation aspect of PCC. You need to have some algorithm for saying, if you sent at this rate and got this utility value, then at this rate it got this utility value, and so on. This is what rate you should be sending at next.
Assuming you're going to talk about PBR and they are doing experiments, probing them.
So actually, I'm not going to talk about it a lot because I'm trying to cover quite a bit. But BBR, I would say, is sort of the opposite approach, in the sense that here, notice the network is literally a black box in the model. I'm not trying to reverse engineer anything about the network. I don't know if now I suffered packet loss because of user mobility or because I'm sending through a cellular network or because there's congestion. In BBR, it's a white box model. Right? You have you're trying to model the network as a single link, and you're trying to explicitly estimate the parameters of that link.
Sure.
So I think that is where the key difference lies.
So you just care about the utility you get and you just change your
Yes.
responses.
Yes, and I think this goes back to John's question. Selfishly optimizing, if done carelessly, could lead to horrible consequences. So I also want to engineer global solutions that are good when different selfish users interact with each other. So what are the design challenges here? Because this is more of a framework. One design challenge is, what should the utility function look like? The other design challenge is, what should the rate control algorithm look like? So even if I have a utility function, I need to decide what rate I should choose next, based on these past experiments. Intuitively, the utility function should do two things in parallel. It should capture application performance objectives. If your application cares more about latency or is more resilient to non-congestion loss, that should be reflected by the utility function. But also, it should guarantee fair equilibrium for multiple competing users. So a nice way to think about this is, I think what we're really doing here is we're engineering the equilibrium of a non-cooperative game, right? We're all going to interact, but if I choose the utility functions properly, I'll ensure that the only equilibrium of this game is one where we've converged to it, and it's fair, and we haven't caused excessive packet loss, and so on. So this is where the choice of utility function comes in. The choice of the rate control algorithm is about the temporal aspects. I want to converge to this equilibrium. If the network suddenly changed, I want to react to that quickly. This is the rate control aspect of that.
Yes, so sorry, quick question, please. Is there any need for the performance objectives to be mapped into transport layer metrics, or can you actually use application metrics directly?
That's really interesting. I've been thinking about this a lot these last few years, and I think that there's different answers to that. One is, for some applications, you could do that. You could have this cross-layer optimization. Think of video streaming. I have this notion of what's going on in terms of the client experience directly, the video client experience. If I could somehow signal that or combine that with the transport layer statistics, maybe I could do more. The other one is, maybe at different time scales, I could also do that in the backend. Right? Even not, for the session running now, but change the configuration of the transport protocol over time. The issue is that either way, you have to combine these carefully because the time scales are very different, right? So think of a video chunk. A video chunk is seconds, right? In the meantime, the transport layer has made a lot of decisions about the sending base, right? So somehow you need to bridge these two.
Yeah, because that's a complicating factor. You have a control loop that's running in the video player,
right?
As a control loop that's running in the transport layer, and this is going to impact this online learning because you might see some variance in the performance metrics being delivered down. That might not be anything to do with the network, but might actually be to do with the control loop running in the player,
right?
Or in the encoding,
right? So the way I think about this is there's two levels of optimization that are possible. One is the one we basically have now, right? If you have TCP or BBR, it's optimizing transport layer performance. Naturally, optimizing transport layer performance is supposed to give you better video streaming experience. Because if I have more throughput and less latency, right, I should be able, the adaptive bitrate algorithm at the video player should take advantage of that. The second layer of optimization is actually explicitly combining the two, right, which I think is a very interesting research direction. Yeah.
How do you ensure that everybody agrees or uses the utility function that you want them to use?
You mean if they're already using PCC, how do I ensure that they're not tweaking the code? I guess that the short answer is it's really hard to enforce, but I think my argument would be we're already living in that world, right? BBR is notoriously unfair to TCP cubic. Browsers open multiple TCP connections because that's aggressive. So I guess you could, if you wanted, build mechanisms to inform you that something has changed, right, et cetera. But my argument would be that that's sort of an orthogonal problem.
Then I have another question, but maybe for later. But
Whenever you want.
The basic idea I'm wondering is, okay, could you do the opposite and have a reward function that tries to enforce that everybody uses the utility function that you want? So
this additional, that's interesting. I don't know. seems like a harder problem. Like dealing with humans and their incentives is it seems like a harder problem. So as John has said, right, you can't just plug in a utility function, and you can't just plug in a rate control decision rule and expect everything to work well. Obviously, if my utility function is I want as many packets to leave me, right, I will cause horrible things. So the key idea is being able to engineer the utility function in a way that it has structure that we can exploit. And this is what PCC Vivace, our most, not recent, but I would argue the most principled PCC variant we have does. It enforces a strictly concave utility function, and then it arguably applies the simplest rate decision rule it can, which is gradient descent. I have a utility function. I want the direction of my rate change and the extent to which I change the rates to be dependent on the gradient of the utility I have, right? If I expect to get a lot better performance by increasing my rate, then I should jump high, right? But if it's the opposite, right, then I should jump low because I'm close to the equilibrium point. And we prove that this actually gives you a lot of very strong guarantees, both locally and globally. Locally, in the sense that even if it's me against the world, I get a strong guarantee that's known as no regret. So even if it's an adversarial environment, I'm the only one using PCC. Even if nature is out to get me, the network is out to get me, there's some guarantees that you still get. But if everyone is using PCC, we converge to a fair equilibrium, whose properties we can analyze. What you're seeing here is a very simple experiment, just intended to give you a notion of why PCC can be helpful. Single link, single sender, the link's parameters change every 5 seconds. X-axis is time. If you knew exactly how the link was going to change, you would have sent at the, I'm not sure what the name of that color is, right? But the light blue, that light blue thing at the top. Right? That would have been your sending rate, right? At the bottom there, you see TCP cubic. Right here, this is not because of congestion. This is not because of competition. You're literally alone on the link, right? It's just because of not being able to adapt to changes.
Got exactly the right link for you. You're looking at Starlink, and every 15 seconds, the latency changes like it was completely different.
Actually, that's super interesting because this is BBR's kryptonite. BBR's kryptonite, as opposed to cubics, is latency jitters. It'd be interesting to see.
You're trying to optimize latency, it's not working. We should have a discussion.
I would love to discuss.
Yeah.
So what you see there, the dark blue is PCC. It's doing well here because it doesn't try to reverse engineer the network model. Right? It literally just tries to figure out what empirically the best direction is. This is PCC in action. This is based on millions of hours of actual video streaming to live customers in the US, multiple locations, Seattle, Manhattan, Cleveland, and so on. What you see on the right is the improvement in terms of video bitrate. So 34% more sessions were supported in HD. What you see on the left is the reduction in rebuffering ratio in the time, the fraction of the movie spent in video rebuffering. And these are the benefits of a utility function, right? So what you see, this is a super simple experiment. Again, one link, TCP connections at the top enter one after the other. What you see here is TCP fairness. This is what TCP fairness actually looks like. Right? It's fair in the sense that if you were to look at the average, right, you see that it's really well behaved. But of course, even when alone on the link, we have this erratic behavior by TCP. Here with PCC, you actually see the convergence to the equilibrium, right, at the different stages, because it's employing the gradient, because it doesn't have these jumps.
Just out of curiosity, what happens if you have a mixed profile where there's competing algorithms? Is it
So-
still converging that way?
So with competing algorithms, it can't converge because in that way, right? In the sense that, because think of if you're in a world where there's TCP cubic and it's suddenly going to decrease its rate by half, right? Any reasonable protocol would try to take advantage of that. But what you will see is fairness or friendliness towards the other connections if you chose the utility function parameters correctly. And the nice thing about this is that it's configurable. You can actually decide on, right, that one of the banes of congestion control is that if you want to be latency sensitive, right, you would be killed by cross traffic that's purely loss sensitive, right? And so, yeah.
So what we saw in the previous plot was essentially PCC adapting to the increased capacity that you were providing
Yes.
in the simulation.
Yeah.
I suppose using this example, it would be identical, right? So as soon as say, a BBR or whatever step back,
Yes,
PCC would fill that gap.
yes,
And that's what would cause the
right,
situation.
exactly. But the interplay is delicate because PCC is latency sensitive. So if Cubic starts filling up buffers, PCC would start feeling the pain, right? So it's gaining more from the temporal behavior, but you need to engineer the way that the utility function to be such that, you know, under reasonable TCP cross traffic, you're friendly, right? But you're not starved by the cross traffic.
So would PCC react in the same way if capacity was to drop substantially?
Actually, you're seeing that here as well. See, when you see these dips in capacity and you see the dark blue line, right, dropping. And the reason it's dropping so quickly is because it's what happens, that the capacity drops, the buffer starts filling, right? And then it goes down. So we've done a lot of different, we've extended this idea in a lot of different directions. Doing reinforcement learning as opposed to this online learning approach, multipath congestion control, where I can use multiple paths. What I want to talk about very briefly is application-oriented congestion control, which is another thing people have been talking about for a while, but that's really hard to actually formulate. Right? So here I want to deal with what is arguably the simplest problem in this domain. We have different types of applications. They require very different things from the network. I want to look at a very rough division between elastic timing and inelastic timing. If I'm downloading a software update while at the same time having a Zoom call or watching a movie, I care more about watching the movie in HD than I care about the software update, you know, taking a bit longer, right? But today, congestion control is oblivious to the fact that these are two different applications. So what we want is to design a scavenger. We want to design a transport layer protocol that only takes advantage of bandwidth if it's not competing with time-sensitive applications. So what should a scavenger protocol do? It should yield to primary flows. When I'm watching a movie, the software update should wait. It should achieve high performance when it's the only one in the system, right? If I'm only downloading a software update, it should take advantage of the bandwidth. And I think this is part of the power of the PCC framework. It turns out that you can achieve all of that within PCC simply by choosing the appropriate utility functions for the primary flows and the scavengers. If I choose two different utility functions and I prove to you that the equilibrium is such that if there's only primary flows, it's efficient and fair. If there's only scavenger flows, it's efficient and fair. If there's a mix of the two, the scavengers give way, right? That's what you want to prove. So the last thing I want to talk about is applying machine learning to the routing context, or more accurately to the traffic engineering context. So specifically, let's think of big corporates that have their own interdata center network, Microsoft, Google, Amazon, and so on, and Facebook, and so on and so forth. In this case, this is for Microsoft. Every dot here, every vertex is a data center. And this network is an interdata center network that's administered by Microsoft and controlled by Microsoft. And when we talk about traffic engineering, the classical theoretical model is this. We have a demand matrix that specifies how much each vertex wants to send to each other vertex. And we have a capacitated network topology. Now, something that's pretty crucial to the model is we also have predetermined tunnels. Right, the decisions about the routes and how to split traffic across the routes are decoupled. So in this case, think of part of the input as being one can only send traffic to two along either the direct red route or the indirect blue route. Right, this is part of the input. So what is it that we're deciding? We're deciding on the traffic splitting ratios. Traffic from 1 to 2 is going to be split in this manner, for instance. And this is true for any pair of source and destination nodes. Now, there's different performance objectives that I may wish to optimize. I may wish to optimize the total throughput, the sum of flow that actually traverses the network. I may wish to optimize some notion of fairness between flows, or just spread traffic in a way that links aren't too overloaded. The nice thing about all of these objectives is that they're solvable via linear programming. So typically the way this works is, think of the Microsoft network. There's a centralized controller. It has a global view of the network. It literally sees a picture like this, and then it runs an LP solver and outputs a traffic engineering configuration. So here's where machine learning comes into the picture, right? You don't know the demand matrix. How would you know the demand matrix? That is, you make decisions, say, every 5 minutes. You don't know exactly how traffic is going to behave in the next 5 minutes. You don't know how much traffic each node will want to send to each other node. So the standard approach is predict the demand. Right? So suppose you have demand matrices from the last hour at 5-minute granularity, so 12 demand matrices. Plug these into some demand predictor to try to predict what the demands are going to look like over the next 5 minutes. Once you have that, we just reduced it to the previous line, right? Now you can just plug this into the LP solver alongside the topology in the tunnels, and you have your traffic engineering configuration. So this is great, with this exception. Okay? What you see here is traffic between a pair of data centers within Microsoft over the course of a week. The orange is the actual traffic demands at 5-minute granularity. Notice how well behaved these are, right? There's very clear diurnal and weekly regularity. Even the weekdays look the same and the weekdays look the same.
Mirroring a map.
I'm sorry?
Mirroring a map.
That's right. That's right. And at the bottom, you see the variance across weeks. This is pretty amazing because if you tell me what happens now, I can tell you pretty much what will happen a week from now at the same 5-minute interval.
Do you have insight into what's running in this data center?
Yes, yes. And I'll tell you what that is. This is customer-facing traffic. So what's running here is Microsoft sending to Microsoft, right? Basically, what's running here is Microsoft sending towards external clients. Naturally, that is much less predictable because it's triggered by external things. So notice that there's still regularity, right? It's not random.
Yeah.
Not completely random, but it's much more variable and it's much harder to pinpoint what the exact regularity is.
And to clarify, customer facing is things like Bing.
Yes, yes. Anything that that is triggered by users external to Microsoft, as opposed to say replicating databases.
I'm surprised Bing isn't just at 0.
That's the aggregated traffic. That's the aggregated traffic. There's other
Actually,
things.
if you retake this in the last 3 months, you'd see all the ChatGPT things, right?
Now this is becoming or the dominant share of traffic, right? So you can tell why when we think about the prediction-based approach, it has 2 problems. One is inaccurate predictions, right? If there's so much variability, if you make the wrong prediction, it's garbage in, garbage out from the LP solver's perspective. The other is that the networks are becoming bigger. So even solving the LP is costly. And even for a fairly small network, you have a lot of variables. Right? Once people are starting to talk about hundreds or thousands of nodes, it's becoming a real challenge. We've seen a lot of recent work just about that, just about accelerating the LP computation. So the key idea in our work is remarkably simple. It's cutting the middleman, right? Instead of explicitly predicting the demand matrix, why don't you look at the exact same input, say demand matrices from the last hour, but try to predict traffic engineering configurations that will fare well. So that's not, you're not trying to predict what traffic will look like, you're trying to explicitly output traffic engineering configurations.
And do you have to separate out the customer facing traffic into a different model and the?
No, because if there's a sufficient regularity, right, you could behave differently for these anyway when you learn. So I'll give you some intuition for that. But here's an unexpected bonus. One is the obvious. The learning objective here is what the network operator actually cares about, right? So you're actually measuring the learning component based on the end result and not based on, it's very hard to define what a good prediction of a demand matrix is, because maybe I've predicted a demand matrix in a way where I'm almost accurate for everything except for one flow that's really hard to carry in this network, right? So here you're actually measuring yourself based on the end-to-end optimization objective, but also an unexpected bonus is you're no longer running an LP, you're invoking a statistical model. This can be orders of magnitude faster, and is, right? Invoking a DNN is order of milliseconds, right, versus seconds or minutes.
So how do you measure,
Sorry, go ahead.
how do you measure, to what extent your prediction is good?
Based on the actual performance objective. So let me actually, here's,
I guess,
yeah.
the flip side of that is maybe you to support SLAs and your DNN gets it horribly wrong for the surgeon who is operating on someone, then
Yes,
as LP, you kind of know what's.
I think that the issue about the LP is it does what you want based on the input it's getting. Right, so
Sure.
it's really hard to argue, right? That
Yeah.
I got low latency, but I was
fair enough.
1.5
Yeah.
away, right, from
fair.
the demands I
Yeah.
was expecting.
Yeah.
So let's zoom in on the learning components of these two things. By the way, don't direct optimization for traffic engineering. So let's zoom in on these two components. In the demand prediction based approach and in DOTE, we have the same inputs. The inputs are just the empirically observed demand matrices from, say, the last few months. Right, so I know in the last few months that these are the demand matrices I've seen. Right, so when I'm training the demand prediction based approach, for example, I know that after seeing these 12 demand matrices, this is the demand matrix I actually saw in the empirical data. The difference is in the performance metrics, going back to your question, Ignacio. Here, for the demand prediction based approach, I need to use some notion of, say, distance between matrices, right? Which is very, it's distinct from the end-to-end objective, and it's hard to correlate the two. Here, the loss function is going to be the actual distance from the optimum in hindsight. Right? If you wanted to maximize the throughput, I know what the demand matrix was. I know how much throughput you could have gotten in hindsight. You'll be penalized on how far you were from that. So the nice thing here is that we're basically doing this is the knee-jerk reaction. Right? This is stochastic gradient descent. We're not applying anything sophisticated. This is actually useful because there's off-the-shelf tools for robust and resilient stochastic gradient descent, which we're using. But I want to give you some intuition for why this provably works, and then I'll show you some results from the field, or not really from the field as much as from experiments, but here are some results for why this works. Here's a simple scenario. A and B want to send traffic to D, all lane capacities are 1, okay? These are the tunnels. A can only send along the blue routes, B can only send along the red routes. At the beginning of each time epoch, think 5 minutes, traffic splitting ratios must be determined. So this is what the traffic engineering system does. It decides how A's traffic to D will be split and how B's traffic to D will be split. And this is the actual distribution from which the traffic is sampled. With probability 1/2, A wants to send 5/3 and B wants to send 5/6. With probability 1/2, it's the opposite. Okay, now something crucial here is, you know this, I know this, the traffic engineering system doesn't know this, right? It's not part of the input, right? It's just seeing empirical consequences of this probability distribution. For the purpose of this example, and this is not a coincidental choice because it's going to be easier to explain this way and then things are going to get more complicated. think of this, of the standard, or the classical traffic engineering objective of minimizing the maximum link utilization. So I want to minimize the load on the link that suffers the most, where load is the flow divided by the capacity of the link. Okay? So in this example, suppose that WAD is the fraction of AD's traffic that of A's traffic that I sent on the link AD. The load on the link AD will be this fraction times how much A actually wanted to send to D. Right? This is how much is going to traverse the link. So here's a cute observation. Suppose that we were to plot the objective as a function of the splitting ratios. So the x-axis here is WAD. There's only two routes, so that uniquely determines how much is going to be sent on the other route. The y-axis is WBD, and the z-axis is the expected maximum link utilization. Notice how well behaved this is. Right? This is a convex function. So if we were to just start anywhere and do gradient descent, we would converge to this red dot over there, which is the optimal solution. The problem is that we don't know the distribution, so we don't actually know this function. Right? We can only infer things from the data. So we don't know the distributions, and so we don't know this function. But here's a cute observation. For any specific demand matrix, we can compute the gradient of the traffic splitting ratios. Because we can do that for any specific demand realization, if we average over these, we're approximating the expected MLU gradient. Just to make this a bit more concrete, let's talk about a specific demand realization. A wants to send 5/3, B wants to send 5/6. For this specific demand realization, I know exactly what the function is going to look like, right? Let's think of the link AD. The load on the link AD is going to be 5/3, how much A wants to send, time how much it decided to send on the link, WAD. Right? I have this explicit formula, meaning that I can also explicitly compute the gradient. Right? If I do this for sufficiently many demands and average over these, I'm approximating the expectation. This is what's known as sample average approximation in stochastic optimization. One thing I want to notice, all the stars are aligned for us here. Typically in networking problems, you don't know what would have happened had you chosen differently, right? Here, because I know the demand matrix in hindsight, I know the exact equation. This is what we're taking advantage of here. So there was nothing about this example that was specific to this topology, these specific tunnel choices, this specific distribution over demands. This is easily generalizable to arbitrary topologies, tunnel choices, distributions. But you know that I lied to you when I said that this distribution is fixed, because we've seen how it changes over time. This is where the deep learning comes in. So don't think of DOTE as optimizing the traffic splitting ratios directly. It's optimizing the parameters of a statistical model. In our case, the DNN, that maps the recent history of demand matrices to the traffic engineering configuration.
So could you end up, the stochastic gradient is probably not going to converge in one step, right?
Right.
What if the demand matrix kind of pathologically changes such that the optimum that you take now is actually the wrong thing to optimum direction that you go down now?
So think of this training is happening offline. Right?
Okay.
So, and the input to the model, right, after you've trained it, you see the most recent K demand matrices, and you output the traffic engineering configuration, right?
Yeah.
So the model should learn, so long as it's, that the environment hasn't changed drastically. It should learn this mapping itself.
I assume that the service operating in the data centers are relatively fixed, and you'd know as an organization if there was ever change.
Right.
So you can select K based on whatever.
Yeah. The assumption here, right, is that there's some, I didn't go into the model, but think of this as a bounded Markov process. There is some K for which, if you were to look sufficiently back into the past, you would get sufficiently many hints as to what a good traffic engineer can do. So this was about minimizing the maximum link utilization, but But what about other objectives, like maximizing the throughput, maximizing some notion of fairness? So here we have to introduce additional things into the traffic engineering configuration, because if, for example, I want to maximize throughput, I can't just let everyone send as much as they want. So you have to also have rate caps. The issue is, without going into the details, you lose the structure. You would have want this to be concave and beautiful, and it's not concave, but it's still beautiful, right? Meaning the induced functions are no longer concave, as in our example, but they're quasi-concave, which is this esoteric thing that EE people know about, for which some variant of gradient descent still works, right? So the key technical depth of this paper is actually being able to prove that this is the case for all of these functions. And then we get that the same type of stochastic gradient descent algorithm would still give you optimality. So the last thing I want to cover in the limited time I have is very few empirical evaluation results. We've evaluated DOTE extensively on different network topologies and different production networks, including Microsoft production networks, several different tunneling schemes, shortest paths, edge disjoint, and so on, and different flow optimization objectives. And we've contrasted it with different proposals from recent years for this task, demand prediction, but also oblivious routing and reinforcement learning and others. What you see here are our results for different WANs. This is the x-axis, contrasting DOTE with other approaches. But I don't want you to actually look at the other approaches. This is normalized by the optimum. So one here is the optimal performance. And because we're minimizing maximum link utilization, we want the performance to be low. And this is the maximum link utilization. So actually, the thing that I think is interesting here is how close DOTE comes to the optimum, which is to be expected because it's provably optimal. But it basically shows that despite having a DNN, which is a function approximator, and despite having finite training data, you can still get pretty close in practice. These are the results for maximizing throughput. DOTE contrasted with demand prediction. And this is a result I like. This is performance under link failures. So we've contrasted DOTE with demand prediction, but also with an enhanced version of demand prediction that has knowledge of which links are going to fail, right? So this is like demand prediction with Oracle knowledge of future failures. Notice that it still loses. I think my takeaway is not knowing the demand hurts you more, right? You can than not knowing the future failures. It's
Sorry, just to make sure I'm reading.
yes,
So DOTE is red.
DOTE is red.
Link utilization in the case of failures is dropping down to below 10%. Is that how I should read it?
One is the optimum. So for link utilization, you're measuring the maximum of the flow divided by the capacity. So in an ideal world, and you're normalizing by the optimum. So in an ideal world, it would be one.
Got you.
Right? This is as opposed to the throughput maximization where you would want to go up. Here, lower is better. Yeah, sorry, I should have made that explicit. So I want to conclude with other research directions that I'm very intrigued by, but I won't have time to go into now. But when we are unleashing the power of deep learning, right, on problems like traffic engineering, this wasn't the case for congestion control. There was no training, there was no deep learning. It was all algorithms with provable guarantees. But here we're using a deep neural network because we want to handle temporal patterns. When we're unleashing this power, we need to have safety nets. Right? We know what software acceptance tests are for traditional software. It's not clear what these are, right, when you plug a DNN into your system. Right? So this is something I've been intrigued by recently. One option is robustifying the training process. Right? Maybe if I introduce bizarre situations, it will just learn to be more robust. Other things I've been experimenting with are formally verifying machine learning-based systems. Before I deploy, could I run sanity tests? But these wouldn't be tests. These would actually be provable guarantees that under no circumstances will this thing output something that I don't expect it to output. I think of congestion controllers. When you're suffering 90% loss, under no circumstances should you increase your sending rate. Right? Or there are some sanity tests that we can define. online defaulting to a safe alternative. In real time, can I tell that I'm making wrong decisions? If I know that I'm no longer in Kansas, I should be doing something different, maybe reverting to the manual solution again. So to conclude, learning-driven networking is still in its infancy. In fact, we have yet to learn to what extent it's going to revolutionize the field. And I think there's many fascinating open questions in this area. So again, thank you very much.
Thank you. It's been a while since we actually did physical plan. And hybrid one.
You can still press the icon on Zoom.
More satisfying. than-
Yeah.
I think we have been making all the questions from here, or maybe it's a good
Maybe we
moment to see if there are questions from the online audience.
Yeah,
Otherwise, I'm sure we can come up with some.
there's one comment that I see from Alireza, which says that it looks like the stuff that you've been talking about looks a little bit like application-defined networks, which was one of the papers in this context.
Cool. I'll take a closer look. I'm familiar with the people that I need to dive in more.
KK has a question. Do you want to unmute yourself? And ask?
Hi. Thank you very much for your talk. It's Ken Liang at Imperial College. I would like to ask you about the PCC work you mentioned. My understanding is the TCP protocol by the work like Stephen Lowe and others has already shown TCP is a distributed algorithm for certain utility function as optimization objective. I wonder in your approach, I see that you're using reinforcement learning. At the end, are you saying that by treating each flow controlled by distributed reinforcement learning agent effectively with certain appropriate assumption on the utility, you actually can have a distributed solution for the reinforcement learning algorithm?
So thank you. So I think there's so the work you mentioned, right? There's a lot of classical work on NUM, right? On the NUM framework.
Right.
Utility optimization.
Right.
Beautiful work, starting with Frank Kelly and through the fast TCP and so on. This is different in a sense that if you think about that work, right? You have a utility function, and they show that you're solving a convex program through the interaction of the end host algorithm and the algorithms being executed at the routers.
Mm-hmm.
Right? That is the dual variables correspond, right? So there, you both need the participation of the network, right? You need the network, the queue management at the router to behave in a certain way to converge. But also, to compute the optimum, you need everyone to be optimizing according to this utility function.
Right. That's true. That's true.
Theoretical foundations for PCC also use a utility framework, but it's a different one. So think in the online learning theory world, you have a decision maker that's selecting between actions, and it's faced with an adversary, right? So you're not assuming, only in hindsight does it see the consequences of its actions, and you're not assuming that these consequences are by a rational player, by other players of the same form, etc. And what you're trying to do is to minimize the difference in hindsight, the distance in hindsight between you at the optimal solution in hindsight. So this is more of a game theoretic approach where I want to ensure that if all of us use PCC, then yes, we'll converge to a fair equilibrium. But if I'm the only one using PCC, I can still give you provable guarantees. Right, so it's a different theoretical thread.
Okay, but let me clarify one thing: you do have utility. Is the same utility used by different users, or you have different users can have their own utility functions?
So it could be. You need to be careful about how you do this. But if you think about my scavenger example, right? Yes. In the scavenger example, you had primary utilities and scavenger utilities. Okay. And what the scavenger paper showed is that if you only have primary players, you get one equilibrium that you want. If you only have scavenger players, you get a different equilibrium that you want. But if you have a mix of both, then the scavengers are basically going to allocate bandwidth, right? To release bandwidth to the primary flows. So I think this is part of the power of this utility framework, that you can engineer equilibria if you do it carefully that are desirable across applications.
Okay, I understand what you're saying. I think in nutshell, I think at the end you have Nash equilibrium or some game theoretic equilibrium
Exactly.
instead of one single utility objective function. Yeah, that's fine.
And you're also optimizing it using a very specific dynamic. This is not primal dual, right? This is,
I understand.
Yeah.
I understand. Thank you.
Thank you.
Any other questions from anyone? So maybe one question, like a broad question from my side. So I mean, you covered two really classical problems: congestion control and routing, traffic management, and so forth. Do you see any differences? You alluded to it at the very beginning. Is one more suitable for certain kinds of machine learning, do you think, versus other? What?
Yeah, so thank you for the question. I think that no, this is I'm not covering the failed attempts. Right? But there's
Yeah.
quite a few, right? And the reasons that these attempts failed was precisely because of what you say, right? Sometimes you're using the wrong tool for the job, and you're either overkilling or underkilling. I'm not sure if there's such an expression, but the reason that we've converted to these very different frameworks is because in congestion control, you have to operate really quickly. And I think it's very hard to argue that there's actual stochastic regularity that you can take advantage of in real time. Right? I'm about to choose a rate for the next 10 milliseconds. How statistically sound is the information of just seeing, right? To get. So this is why we've taken the very worst case game theoretic approach. On the other hand, when you look at the SWAN traffic engineering example, sort of the exact opposite. This is, you make decisions after 5 minutes, right? After collecting a lot of data from a lot of flows, you have time to globally optimize. So I think it all boils down to, you know, the nuances in the definition of the problem, even within routing, right? If you were routing, if you wanted to replace OSPF with something that's machine learning based, I'm pretty sure it would look nothing like this framework. You don't have the centralized controller, you're making decisions quickly. I'm not sure what the regularity translates to. I think this is why probably you need to tailor a solution to every context.
Every problem its own specific solution.
Yes.
That's a good one. And there are any final questions? You're slightly past 1700 now. So if there are no other questions, then we thank the speaker.
Thank you very much. Have a
Pleasure. Thank you for being here.
Thank you.
Thank you.
Thank you. Bye.
Bye, everyone.
Bye.
Well, we can make the rest of questions in the pub.
I'm not, I think the quality of my answers maybe will improve actually.
It's
Very true. Definitely true here.
Yeah, you actually kind of gave the answer to something I was going to ask you before I did. What's the right moment in which you switch from your deep learning solution to the, let's say, traditional algorithm?
Right.
Which was reminding me, in trains they have what they call the dead man switch.